Good morning, everybody, and thank you for attending this nice symposium. And very happy to be here to talk about S parameters and EMI and EMC filters. So I hope you see my screen perfectly. It's the title. I am Arturo, like Florian was introducing. I am at the University of Zaragoza in Spain. And let's start talking about S parameters. In the slides you will receive, you will have information about my laboratory and my contact address in case you have some question related with the presentation or with any EMI, EMC subject. And let's start with the S parameters. Well, what are S parameters? Consider you have any kind of network that is linear. When I say linear, it can be passive or active. An example of a passive network is a cables with connectors, or cables, connector, PCB traces. That is because S parameters are usually used a lot in signal integrity problems when you are analyzing the good or bad path for your signals to minimize the possibility to have signal integrity. Examples of linear passive circuits are filters. The filters we are building with inductors and capacitors. Examples of active networks could be amplifiers, but amplifiers when they are working in a linear way. For example, a class A amplifier could be analyzed with S parameters. But in the moment you start to work with some kind of non-linearity, for example, you have saturation in inductors or you have saturation in your transistors, the possibility to work S parameters is limited, and you need special S parameters for nonlinear systems. Today we will be talking about S parameters for linear systems, and the filters we will be analyzing are linear. So how we are able to characterize this kind of networks? From circuit theory point of view, especially for the people that is familiar with low frequency design, we have several parameters that are named C, Y, H parameters. These parameters work in different ports of your networks with voltages and currents. When we talk about these parameters, we are working with N ports. You can have this analysis with one port, for example, the input port of a component, or we can work with two ports. In a filter, we have the input and the output port, or we can work with more ports, like, for example, mixers or more complicated networks. When we are working with these ports, considering the figure, we have two ports, like in the case of a filter, the voltages and currents can be considered excitations or results from excitation. That means we have independent variables or dependent variables. If in the case your independent variables are currents, I1, I2, I1, I2, currents at the input port 1 or the output port 2, the idea is that dependent variables will be the voltages. So we are able to have find some kind of relation between voltages and currents with several numbers. You can see here the C11, C12, C21, and C22 that are in the units of ohms. That is because these parameters are called the C parameters, or the matrix is called the C matrix for this analysis. For calculation of these parameters, we need to consider that they are complex numbers. We have module and we have phase. So we will come back later to this. So how is important this? Because for complex networks, or with networks where we have a lot of components, or we have a lot of parasitic effects, or we have a lot of different connections between these components, we have the possibility to represent the behavior of the circuit with the external world with like a black box. You don't need to understand what is inside of the blocks, but you will be able to predict what will happen when you connect this block to any other element. No? If we are interested in considering independent variable, the voltages, then the idea is that with the voltages like independent variables, the dependent variables will be currents. That is because this matrix is the Y matrix. And the H matrix, H came from hybrid hybrid, the idea is that we have some of these parameters, H11, H12, H21, or H22, are with units of Siemens or with ohms. That is because the name is H matrix, hybrid matrix. How we can calculate these numbers? Let's consider that you have calculate or measure. Let's consider that you are interested in obtaining H11. The idea is to go to the expression of H11 and to find that H11 can be calculated, simulated, or measured if you specify how is the ratio between the voltage at port number 1 divided by the current at port number 1 when the voltage in port number 2 is 0. That means what? You need to take your network and you need to create here a source circuit. So what happened with H, C, or Y parameters? To extract the value of the parameters, you need to create in your network input, output ports, source circuits or open circuits. And we have several limitations for this approach. The first approach, if you are working in high frequency, is that voltages and currents are more difficult to measure if we are working with power and impedance. The second important thing is that to create in high frequencies short or opens make difficult to implement a practical circuit because many systems, especially active systems like amplifiers, can be unstable, can oscillate, and you can destroy the circuit under test. And sometimes networks with open and source circuits at the input or the output port can oscillate. That is because S parameters were created. The idea of S parameters is to be able to work with terminal impedances that are not open or source circuits. We will work with a known impedance that, like a reference, is usually 50 ohms. So is S parameters a technique that can be applied only for high frequency? No. From circuit theory point of view, you can apply S parameters from very low frequencies up to very high frequencies, like with the other parameters, but they are more common to be used in high frequencies. So let's see how we can consider the use of S parameters. Instead of working with voltage and current, we will be working with traveling waves in a transmission line. So consider that your system has a transmission line at the input port and a transmission line at the output port. These transmission lines, think about, for example, coax cables, have 50 ohms characteristic impedance. And you excite in one of the ports and you terminate the other port with the same characteristic impedance. In a practical world, this impedance, this C0, is usually 50 ohms. So we consider that the energy that is able to go out from the source will be traveling through the transmission line, and if the input of your network is exactly the same reference impedance, nothing will be reflected. If this impedance is not 50 ohms, is not the reference impedance, part of the energy will be reflected. This is V1. So what happened with the part of the energy that is going in? The part of the energy that is going in will be able to go out in the output port. If you arrive to a terminal impedance that is the reference impedance, nothing will be reflected. When you want to measure the parameters, you excite the input port, and when you finish the measurement, you switch the output and the input port, and you excite the port number 2 while you terminate the input port with 50 ohms. In this way, you are able to measure the waves that are going in one direction and the waves that are going in the other direction. From the mathematical point of view, these waves are not specifically voltage or current. They are voltage, reflected voltage, or incident voltage normalized to a known impedance, to the known impedance, that is 0. So A1 is the maximum power, is the maximum energy that you will be able to extract from the source if you terminate the source with the same C0. So when you specify these waves, A1, A2, V2, and V1, in this way, with the voltage that is in incident, that is because you see the I close to the V, or the reflected voltages, normalize it to C0. When you calculate this value square, you will have the units of power. So with these numbers elevated to the 2 power, you have power in your in the signal you are working with. If you have a low frequency and you have a traveling wave, you can apply the same idea, but the idea is that you will not obtain the maximum power from the source, and then you create some kind of imaginary reflection that will create the same situation like you have with your lamped circuit. No? So let's consider that you have these parameters. With these parameters, S11, S212, S21, and S22, you will be comparing the signals that are being reflected and the signals that are being incident in your network. You have different ports, so that is because the S parameters are called scattering parameters, because they try to explain how the energy that is going in one of the ports can go out to the different ports of your network. No, they spread around. The parameters must be specified specifically for some reference impedance. I repeat that this reference impedance is usually 50 ohms. These S parameters, like the other parameters, are complex numbers. You have module and phase, and it's very easy. Usually you can do this easily by computer, with any simulator, especially if they are for radio frequency analysis, you can calculate one parameter from the other. So how we can understand what are S parameters from a physical point of view? If you consider that the way to talk about the S parameters is that if the port number 1 and the port number 2 are in this way, S11, or let me start with S21. The idea is that when you write SIG, you are referring with I is the output port and G is the input port. So for example, S21, what is S21? Is the transmission gain of the network from port number 1 to port number 2. The idea is something like the S21 is giving you the information about how the energy is able to go from 1 to 2. If the network is passive, this energy will experiment attenuation. If the network is active, probably, if this is an amplifier, you can have some kind of gain, decibels of gain. If you calculate how much is S11, S11 is the ratio between the energy that is going to the port number 1 and is being reflected. So S11 is the reflection coefficient at the input port. That is a very important information to measure how is the input impedance of your network, because you know the reference impedance. So you have the reflection coefficient relative to a reference impedance, you can calculate how is the input impedance of your network. So S11 will be the input port reflection coefficient. S21 will be will give you information about the transfer of energy from input port to 1 to input port. And S12 is the opposite. S12 in a symmetrical filter will be the same like S21 if you terminate in the same impedances, but for example, in one amplifier, S21 can be very high, but S12, the green arrow, the possibility to pass energy from 2 to 1 must be not easy to obtain. And finally, S22 will be the reflection coefficient at the output port. So with the 4 parameters, you have the possibility to represent your network like a black box and to discover what happened when you introduce this network in some specific environment. In reality, what happened when you connect this network to other different circuits. So this is what we will try to explain with some demos, and we will be using the Bode 450 is the instrument from Omicron that is able to arrive to 450 megahertz. And to explain or to introduce the S parameters, we will start using a commercial filter. No? So consider, for example, that you are interested in this filter. This is a typical filter for radio frequency application, wireless communications, or perhaps medical application, things like that, but when designers are working with known terminal impedances. This is 50 ohms. That means what? You have one input port, you have one output port, and both ports are prepared to work with 50 ohms terminal impedances. And the manufacturer, in this case, many circuits, give you the response of the filter. This is attenuation. If you want to plot like the gain of the amplifier, and this is frequency, is the mirror image of the filter, no? So this is 0 dBs, and you will be attenuating minus 40 dBs at some specific frequency. If you specify attenuation, you see that the curve is mirrored, and you obtain more attenuation as you increase the frequency. And this is the filter I will be analyzing. So let's switch to the camera so you can see the Bode 450. Okay, so I have a port number 1, I have port number 2, I have 2 coax cables, and at the end of these coax cables is where I will be connecting the filter, no? But before connecting the filter, we need to make the calibration of the system. Calibration means that we will be able to translate the reference planes from the input port of the instrument to the end of the coax cables. In the same way, we are removing the losses and the frequency response of this network. If you are introducing in this path some kind of attenuator, amplifier, or something like that, you will be able to normalize, to calibrate, including the losses or the gain of the element you are introducing in the path of your signal, no? So now that you see how is the instrument, let's switch to this camera where we see the end of the cables. Let's move this one this way. Okay, this way. So these are, you have here let me,
Arturo, I don't want to interrupt you, but we still see the filter curve.
Okay, sorry, this one. Now,
yeah,
sorry.
Thank you.
Thank you. Give me, there is a lot of things in the laboratory, a lot of cameras, lights, and sometimes it's difficult to avoid failures. So you see here the port number 1. This is the port number 1. Let me switch in the other direction. Okay, this is port number 1, and this is port number 2. How we do the calibration? To do the calibration, we connect one with the other with the best connection we have. Because this is 50 ohms and this is 50 ohms, I will be using a barrel, a connector, that is 50 ohms in characteristic impedance. So now we open the software of the analyzer, okay, you can see here, and what we find is the possibility to specify some specific frequency range. This is the frequency range I will be considering. Let's go to the other window here. And I am going to start, for example, in, I don't know, 10 kilohertz or 100 kilohertz. And we finish at 150 kilohertz. This is a filter for around 150, for around 50 megahertz. So let's see the calibration menu. We perform new calibration, and no, sorry, I am in the wrong measurement. We go to the vector network analysis. We select the transmission reflection. You can see here the block diagram. We excite the network with port number 1, and we receive the signal in port number 2. We select the measurement. Sorry, I had to select it and other measurement in the analyzer. So now we specify here from 100 kilohertz, for example, to 150 kilohertz. Now we open the calibration menu. Let's go here. And then the software gives me the possibility to calibrate with the through option. I don't know why you don't see this menu. Okay, we start here. Okay, the system is calibrating, is sweeping from 150 kilohertz to 150 megahertz. We close here now. And now we remove this trace, the blue color trace, and we put the trace number 1 in more white. And we make a run. You can see that it's a flat response that is in 0 dBs. This is S21. That means what? All the energy that is arriving in port number 2 is exactly the maximum power we can obtain from port number 1. Obviously, we have a 50 ohms output port, we have a 50 ohms transmission line with a 50 ohms barrel, that in theory is perfect, and we have a 50 ohms load port, okay? So now let's replace the barrel with our filter. We put here the filter in the middle. Let's connect the input port. In theory, it's symmetrical, I think, but let me do this in this way. Okay, and let's see what happened with the response. We run the test, and you can see what happened. No? Now we are able to compare how is the response compared with the response from the manufacturer. So you can see that the manufacturer is offering at frequencies, for example, of minus 3 dBs, is around 55 decibels. No, sorry, the minus 3 dBs frequency corner is at around 55 megahertz. No, so let's go here and we go to the cursors. We can take this cursor. We can go to number 3. Here we can write here minus 3 dBs, and automatically the cursor is located in the frequency of interest. It's 53 megahertz. So in this way, you can understand how the filter is working. The frequencies below approximately 50 megahertz are not attenuated, and the frequencies going down are attenuated some specific decibels. Remember, this is in a 50 ohms system. So when we introduce this filter in a wireless communication system where the first module is a 50 ohms source and the next module is a 50 ohms load, the system will be working exactly like you are seeing here. Why the filter is working? The filter is working because if we specify trace number 2 and we put trace number 2 in more wide, sorry, I need to go to this menu here, okay? And we repeat the test, we will see now in the screen S11. So in blue color, you see S11. So what means that S11 is in blue color is close to 0 dBs in the high frequency range. Remember, S11 is the reflection coefficient. So at this frequency, we have a lot of attenuation because at this frequency, we have here close to 0 dBs in reflection coefficient. 0 dBs in reflection coefficient in port number 1 means that all the energy trying to go into the port is being reflected. This is what happened with filters, including inductors and capacitors. Energy don't disappear. Energy is reflected to the source. So here in the band, in the area where the signal is able to pass, the idea is that the blue signal is below minus 40 dBs, more or less. Like a general rule of thumb, if you have in S11 better than minus 10, minus 15 decibels, you have a perfect match. That means that 95% of the energy trying to go into the port is able to go into the system. So we don't have reflection, okay? So 0 dBs means full reflection, minus infinite in S11 means total absorption, no? So in a practical way, you don't need to go to minus infinite in the blue curve. You are below minus 15, you have a perfect match. So what happened if you go in the slides? If you go to the slides, I am not going to explain here because if not, we don't have time. In the slides, you can see that I have introduced another example over our low-pass filter with a filter that is prepared to filter FM band when, for example, broadcasting stations are destroying your circuit. No, you look at this in the red color line, you have S21, in the blue color, you have S11. So you can see that this filter is removing the energy between 88 and 108 megahertz, the FM broadcasting band, because in this frequency range, all the energy is being reflected in port number 1. So this is when we work with 50 ohm filters. So what happened when we are working with EMI and EMC filters? All the people that is usually working with EMI and EMC filters know that it's not possible to work with 50 ohms termination. Usually terminations are unknown. So let's see with one example how we can understand the use of S parameters for EMI and EMC filters in a very fast way. So to do this, what I am going to work is with LTSPICE. So let's consider that you have this filter. With this filter, I have one inductor and one capacitor, 4.7 microhenries, 5.7 nanofarads. We have a 50 ohm system. This is the way that many people is designing filters. Remember, in EMI and EMC, probably you don't have 50 ohms. No, I am sure that you don't have 50 ohms because in one of the, consider for example, that the source of the signal is the differential mode behavior of your power electronic circuit. How is the output impedance from 9 kilohertz to 30 megahertz where you are measuring conducted emissions? It's unknown. Usually it's very difficult to specify how this frequency, this impedance is. Additionally, is resistive or is capacitive, inductive? You have resonances in the output impedance? And what happened at the other side, in the load? What we have usually is the line impedance stabilization network. If you are measuring differential mode emissions, probably you will use here instead of 50 ohms, 100 ohms. Or if you are measuring common mode emissions, this impedance is 25 ohms in a typical listen. So how you can use S parameters in simulation? If you have some kind of radio frequency software in your laboratory, probably you will be able to import S parameters. If not, you can work in LTSPICE with the command .net. With .net is a command that is has the possibility to work with S parameters in some way in LTSPICE. So let me simulate this circuit. When we simulate this circuit, okay, we can see how is the, let me put this in window vertical. We can go to the output and to see the output voltage. So let's remove the phase, no? So this is the response, the output voltage when we are excited with 1 volt. Look at this, this is minus 6 dBs. Obviously, in low frequencies, inductor is a short circuit, capacitor is an open circuit, and we have a 50 ohm system. So when we apply 1 volt in the ideal generator, in the middle point between 50 and 50 ohms, we have 0.5 ohms, 0.5 volts. That is half the voltage in the source. So this is minus 6 dBs when we introduce this in a linear way. So what happened if we add a pane here? Let me add a pane, and we go to add trace menu. You go to add trace menu, and you can go to specify S21 relative to port number 1. This possibility to plot S parameters, Y parameters, C parameters is because I have been using the .net command. So when we do this, you can see S21. It's basically what I can expect from this kind of filter in an ideal system with 50 ohms. Let's consider that we are interested in some specific components from the market. So let's go to the slides, and you see here that for my 4.7 microhenries inductor and my capacitor, I am using these components from Booth Electronics. I can measure with the Bode 100 or the Bode 450. I can measure the response of the components. You can see impedance and phase. We can see clearly that the resonant frequency of this component of the inductor is around 30 megahertz, 36 megahertz, I think, sorry, and the resonant frequency for the capacitor is around 20 megahertz, okay? From these components, we are able to return to LTSPICE, and we are able to open another circuit. Let's go here, where I am comparing how is the response with parasitics, no? So we have here the ideal filter. Now, you have here the previous ideal filter, and you have here the 2 components with the parasitics. One possibility is to plot the resistance capacitance of the inductor in parallel, manually, directly, or you can go inside of the components and to introduce the parasitic like part of the information of the component. When we run the test, we can see how is the, let me close the previous simulation. Let me open the window and let me put in vertical scale, sorry. And we run the test, V1, and this is V2, and we can remove the phase. Okay, so I hope you see here that the this way. You can see that the parasitics, let me put this so you can see the graphs correctly, this way. Okay, so you can see that with the parasitics in the components, the filter is not low pass, it's a high pass, it's some kind of band reject, because at frequencies over the resonant frequencies of these components, the filter start to be a high pass filter. The inductor start to be a capacitance, and the capacitor start to be an inductive effect. But how is this related with the real behavior of my filter? Let's go to the Bode, again, to the Bode 100 software, 450 software. You can see here, if I go here to the export menu, when you are measuring components or systems, one of the options to export is touchstone export. Touchstone is the format that is used to specify S parameters. I can specify that this is a two-port network, and I can specify for S11 the reflection, and for S22 the reflection. For the other S12 and S21, I specify the gain measurement, and you can specify here the units of the file that will be created. When I save as this filter in my computer, for example, let's go to the this one, to the desktop, for example, I'm going to save this file with the name, let's see, for example, demo, demo S2P, okay? So when I open my desktop file, you can see, let's go here. So you can see, if I open the file, we get this one. You see, this is the touchstone format. So we can have all the information of the S parameters of my filter from the first frequency to the last frequency. And this information can be imported. You can import this in LTSPICE or in any software for simulation. So let's go to the screen of LTSPICE, and let me open, instead of this file, let me open the next step in our simulation, okay? You see here that I have the previous ideal filter, I have the filter with the parasitics, and I have here another one that where I am importing the results of my measurements. And this is very important, because the filter I can measure will be a real filter, no? So let's go to the Bode 450 megahertz, and then let's go to the camera, sorry, and let's go to the camera here, top view, okay, and let's put here my filter, the real filter I will be using, okay? So with the real filter I will be using, I am preparing here some connectors, so I want to test my filter. In an EMI filter, the problem is that you need to work in high frequency, and additionally, you will need, this is my filter, okay? So I am using a demo board from Booth Electronics. You can see here my inductor, you can see here my capacitor with a lot of parasitics, because I have these sockets, and I have some kind of layout, or perhaps close to my inductor, I have some kind of metal structure, no? Let me put this here, no? Consider that this is the enclosure of my product, and I have metal that is close to the inductor. So how is the possibility to measure or to represent in the model the effect of this metal close to the inductor, or the coupling between this inductor and another inductor, or the coupling between two capacitors in your filter, or the effect of the layout of the PC board, no? If you export the S parameters like I have done before, the idea is that you get something like this. You have a black box to represent the result of the filter in a 50 ohm, 50 ohms. And this is what you are going to see. I open the simulation, I run the simulation, sorry, I close the previous simulation, let's put here vertically, and we see how is the S11 at trace, S21 for the first example, for the second example, and for the third example. We plot here, and you can see the difference. Let me remove the phase. Okay, so you see in black color, you see how is the response of the ideal circuit. In red color, you see the model of my circuit where I am modeling only the parasitics of the components. And in blue color, you can see how is the response of the total filter, including the layout and all the elements around the system. So in this way, you can, for example, use this to adjust the values of specific parasitics, or you can identify what parasitics in your layout or in your setup is dominating some specific peak that appear like a resonance. The final thing you can do with simulation is in the fourth example, where I am using the same block, the same blocks. Let me close here, this one, and let me close this one. Okay, so I have the first circuit, the ideal circuit, the circuit with the parasitics in the components. You have here the system I have imported, and now is the same imported circuit, but with the terminal impedances equal to 5 and 100 ohms. So let's go to LTSPICE, and we are going to simulate this. How is the difference between using 50 ohms or introducing my filter in a 100 ohms system? So we simulate, okay. We put this in vertical scale, Windows did vertically, and let's see what happened in the system, in the output voltage, when we work with the nominal impedances of 50 ohms. Remember, we have here minus 6 dBs and here the parasitics. But what happened when I introduce the filter, for example, going to my listen with 100 ohms input impedance with some specific source that is 5 ohms in output impedance, no? So you can see that the filter that was working correctly in a 50 ohm system, like theory is predicting, can find, for example, the possibility to offer some kind of ringing or underdamped response that can be dangerous for stability or can be dangerous for transient behavior or things like that. Okay. If you are interested in the files of this, it's very easy to draw this in LTSPICE, but if you are interested in the files, let me know and I will be happy to share with you the file, the LTSPICE file, okay? In my, I am finishing because we are on time now, but in my slides, I have introduced additional information. In the case you want to apply this technique, you will have pictures of the demo I have done, and with all the comments, so you can analyze this in your laboratory or in your office. Let me know you find some error, of course. And I have introduced this technique that is very useful to combine with your analyzer to be able to specify how to measure differential mode or common mode and plotting the response in S parameters format or in the format you prefer, no? In the top view, you will see that I am using two transformers. These transformers give me the possibility to introduce the filter in the middle. They are one-to-one transformers. So you calibrate in these frontiers, okay, to remove the effect in frequency of the transformers. In this way, when you are measuring differential mode, for example, for line neutral, you are not connecting the lower part of the filter source circuiting because the output of the analyzer is connected to the same Hertz system, no? If you are interested in common mode, ground is ground, and you can use this power divider and power combiner to maintain 50 ohms in the at the ends of the filter, okay? So I hope this will be useful for you, and that's all. Thank you.